Hi, this is Xiang Li, and today I'm going to be explaining mathematical induction. Induction is a proof technique just like proof by contradiction and proof by exhaustion. It's usually used to prove a statement, which could be a formula, an equation, or an inequality, or others, is true for all positive integers. It doesn't necessarily have to be positive integers, it could be negative, all integers, or not even integers at all. But usually you're going to be using induction for positive integers, and if you know how to do it with positive integers, then you'll know how to do it with the other scenarios. Here are some statements that you could prove with induction. How do you do induction? We're going to learn it by example. Let's say you're asked to prove 1 cubed plus all the way up to n cubed is equal to the result on the right. The first step in induction is having a base case. But when I first learned induction, I didn't understand this part, so let's skip it. Skip straight to the induction step where you will find the reason for the base case later. In the induction step, you assume the equation holds for n is equal to k, where k is some positive integer. K could be 1 to 5,000, it doesn't matter, just a positive integer, and you want to prove that that implies the equation holds for n is equal to k plus 1. In other words, you want to prove if the equation holds for n is equal to k, then the equation holds for n is equal to k plus 1. Now, suppose for a moment that you prove the induction step, then here's what will happen. If you substitute k is equal to 1, the induction step would say if the equation holds for n is equal to 1, then the equation holds for n is equal to 1 plus 1, which is equal to 2. Now, if you substitute k is equal to 2, you get if the equation holds for n is equal to 2, then the equation holds for n is equal to 2 plus 1, which is equal to 3. If you substitute k is equal to 3, you get the equation holds for n is equal to 4, and so on up to positive infinity. So, what it's saying is if the equation holds for n is equal to 1, then the equation holds for n is equal to 2, 3, 4, all the way up to positive infinity. But that's only if the equation holds for n is equal to 1, and that's where the base case comes in. The base case is just proving the equation holds for the first starting number. In this case, it's n is equal to 1, and it can be done by simple substitution. 1 cubed is equal to 4 over 4, which is clearly true, so you have proven the base case. Now, we're not quite done yet because we supposed that we proved the induction step. The reason we supposed that we proved the induction step is just explain the purpose of the base case. But now we're actually going to prove it. So we assumed in the induction step that the equation holds for n is equal to k, so this equation is true, and we want to prove that that means the equation holds for n is equal to k plus 1, so we will add k plus 1 cubed to both sides, because we want to manipulate the equation to look like the equation for n is equal to k plus 1. So, top equation implies the bottom equation. Doing some simplification and algebra, you get the result. Now, as you can see, the top equation is the equation for n is equal to k, and the bottom equation is the equation for n is equal to k plus 1. And you've essentially proved that if the formula holds for n is equal to k, then the formula holds for n is equal to k plus 1. And you have finished the induction step. Just to summarize everything, for induction, you first have a base case. 1 cubed is equal to 4 over 4, which is true. And next, you have the induction step. You assume the equation holds for n is equal to k, then you prove that the equation will also hold for n is equal to k plus 1. And for the inclusion, you would say which is equal to n squared n plus 1 squared over 4 for n is equal to k plus 1. Hence, the equation holds for n is equal to k plus 1, and by induction, holds for all positive integers n. And you are done. Here are some examples that you should go through, and thank you for listening.